See, what else do I have to do here to make my computer happy? I'd love to be able to see my notes, but there's something obscuring them. There we go. Okay, great. So, good. I'll proceed. I'll attempt to proceed. So I'm going to give a little bit of background, not pre-Ken, but pre-Ken's graduate career. So this was all at Carnegie Mellon University in Pittsburgh, where I was a graduate student and where Ken eventually became a graduate student. In 1983, I was, two of my advisors left. And so I was looking around to find a new academic advisor, and Ed Clark had recently moved to Carnegie Mellon from Harvard shortly after co-inventing CTL model checking with Alan Emerson. So for me, that was a really lucky break, which I didn't understand at the time, but I came to understand later. So Ed started building a research group, and in that group, I was the second PhD student at Carnegie Mellon. There was a model checker. What?
What's the first?
Bud Mishra, who's a professor at NYU. So yeah, he ended up mostly, he's like a polymath and mostly not doing formal verification, bioinformatics and all kinds of things, algorithms. So the first model checking program was actually written in Lisp. I had the advantage of being an experienced Lisp programmer because of my background. And this program struggled to inspect a few thousand states. I did some extreme hacks to get it up to maybe 10,000 in order to get my first paper, I remember. The first applications were asynchronous circuits. This was a brilliant idea of Ed's, which is find the simplest possible concurrent system that tends to have bugs, which would be the application for, you had a hammer looking for a nail to hit, and this turned out to be an ideal nail to hit for a program that could only handle a few thousand states. Now, Ed, besides being a Turing Award winner, was the co-founder of CAV, the conference we're at. And in 1989 was the first one, and I attended that in Grenoble, France. And the reason for that is that at that time, there was no dedicated research forum for model checking at all. Model checking was a new idea, and it was difficult to find places to publish papers. Maybe we could get one into LICS, which I think we did. One of those papers I'll talk about, Logic and Computer Science, but that was a very broad conference. My impression was dominated by logicians. Many of the papers didn't have a lot of computational content. It was very theoretical and not particularly concerned with whether you could actually verify stuff. Sometimes we get papers in hardware conferences, but a lot of the times they didn't know what to make of it. So this was forming a community of people who are interested in automated verification like model checking. Meanwhile, at the same time, Professor Randy Bryant was at Carnegie Mellon, had just come to Carnegie Mellon about the same time actually, and had invented BDDs. I remember walking to into his office. What?
Rediscovered.
Okay, they were just waiting to be.
No, that was before. AKL's published a paper on this. Rediscovered.
Okay, fine. So anyway, did something with BDDs. I remember walking into his office during a Christmas holiday when there was nobody else in the building. And he said, Dave, maybe you would be interested in this thing I've done. And when he showed me this before it was published. And so initially these were for analyzing combinational circuits. And I remember thinking, wouldn't it be great if we could find a way to apply this to model checking, but I couldn't figure out how to do it. And at that time, just for perspective, BDDs pretty much dominated other methods of solving propositional logic. So I saw people publishing papers about DPLL-based SAT solvers, and they just couldn't handle the same problems that BDDs were, oddly enough. So it wasn't until I think 1995 or 1996 that SAT solvers got to the point where they actually could beat BDDs on a lot of problems. Good. So I finished in September 1987. I think that's when I did my PhD thesis. I had gotten a job at Stanford somehow. I drove across the country and started assistant professoring. I stayed in close contact with Ed Clark, and just shortly after I had left CMU, he said he had these new students, and he had one who was pretty good, this Ken McMillan guy. And so, yeah, I think pretty good was actually the phrase he used. And so I checked this. My recollection is that Ken had come up with symbolic model checking within a few months of starting. And I saw Ken at the airport on the way here and checked it with him. And yes, that was true. And in fact, during the introductory classes at CMU, he'd seen Ed talk and he'd seen Randy talk and thought, oh, maybe you could put these two ideas together. And unlike some of us, he actually figured out how to do it. So I was pretty impressed with Ken's progress with, having gotten a breakthrough in his first few months at Carnegie Mellon, because my career was, I was there for 4 years before I managed to publish a paper at all. And so I feel, and I think there's a general consensus like this, that the early success of symbolic model checking is largely due to Ken. There was CTL model checking, for which people got Turing awards, but that was based on a theoretical paper, nominally the 1983 paper that was cited, and with a list program that could do a few thousand states. And so the ability to do a reasonable number of states was largely due to Ken. So quite a while after he actually got this thing, and after a few other papers had been written about doing BDD-based analysis of state machines, we worked on a paper together called 10 to the 20th States and Beyond. So this is a very heavily cited paper, and it's one that is really founded on Ken's work, although there were several co-authors, one of which was luckily me. And so I think it was, yeah. Licks in 1990, although the one you see cited is from a journal in 1992. So Ken had also, sometime in there, also done the SMV symbolic model checker, which was the first practical BDD-based model checker. And it was, given that it was an academic tool and whatever, well-designed and well-documented and usable by people who are not Ken. And Ken also demonstrated that this method could be useful on practical examples. And the example I remember was the Gigamax cache coherence protocol. As you can see, all of this stuff is clustered around 1990. And the combination of having these interesting theoretical insights, an actual tool that other people could use on problems that maybe Ken hadn't thought about, and being able to demonstrate success on an example of current interest and importance to people who didn't care about formal verification at all, was enough to put formal verification on the map. People suddenly had to start taking it seriously. It wasn't just a theoretical topic anymore. So in fact, there started to be commercial interest the years after that, and people started working on actual tools that they could sell in the electronic design automation industry. So I'm going to talk about this paper a little bit, which I'm familiar with because I worked with the whole team on it. So that was the name. Now, people have mocked this name a lot. And I remember at the time, Ed telling me, Ken came up with this name, but he doesn't want us to use it. And then, of course, Ed had, one of Ed's talents was a little bit of flair for marketing, which is not necessarily, if you knew Ed Clark, it's not necessarily something you would think of, but he couldn't resist using this title. And so that's the title we ended up with. The author order I figured out is, it's a lexicographic ordering by the alphabetic ordering of the school names, and then alphabetical order, secondarily of the authors. But, I know the role that these two guys played. And, you know, mostly Ed and Jerry. And, you know, the basis for the thing was Ken, and I know from the interactions that Ken was kind of the go-to person if nobody else could answer questions. So I feel I credit this paper largely to him. Jerry's not here to complain, but I don't think he would disagree with me. So the stated goal here, and I think, I'm not sure Ken agrees with this. I think actually this was me strategically. That I could see that there were going to be a lot of people writing papers, computing fixed points with BDDs and whatever. And a lot of this was going to get really repetitive. And maybe we should just put a stake through the heart of the whole field. Let's just kill it, you know, by writing the last paper on BDD-based verification. And so that's what we set out to do. And we say it politely here. So we have this general framework of mu calculus formulas. The idea is, next idea you had about verifying something with BDDs, you write the mu calculus formula and you say, that's how you do it, and you're done. And it's a very, very short paper. That's not how it worked out, because it turns out there are lots of optimizations that people do. My animation's going amok here. So if you haven't seen mu calculus, everybody at CAV used to know what mu calculus is, but I know there are younger people here who may not have cared about it. Don't ask me to translate what this formula means. Fairness related, I guess. But the idea with mu calculus is a way of nesting fixed points, writing nested fixed points in a very compact way. And you can write down almost any iterative algorithm involving BDDs, at least the major ones, just with this notation. And you figure out a way to interpret this and implement it in a general way, and then you've got your BDD-based algorithm. What?
What is lambda?
This is lambda calculus. So this is actually defining a predicate with a variable y in it. Please don't ask more about this formula. You know, I have taken formulas like this, maybe this very one, and deciphered it, but it took me a while. And frankly, I don't want to do it anymore. So the problems addressed in the 10th of the 20th states paper. I mean, we have this general scheme for solving problems with BDDs and iteration. And so then we tried to show that it could solve several different problems. And so CTL model checking was the obvious one, if Ed Clark is a co-author, but also propositional temporal logic, where we could do a symbolic version of the Tableau procedure, and observational equivalence between transition systems, and certain automata theory, like inclusion problems between omega automata with certain restrictions on them. And the implicit was lots more, anything else you could think of. So that was that paper, and it's highly cited, I think, because of the generality of the paper and because we tried to do a thorough job on it. And it's sort of the landmark paper that gets cited when people talk about symbolic model checking. So it's got a lot of citations in Google Scholar. I'm running substantially slower than I expected to, so I'll just truncate the talk when I have to. But at the same general time, Ken developed this S&V model checking tool. So there are now nth generation versions of this tool around. I don't know if the original S&V worked, but it was a pretty good tool, and you could use it for all kinds of things involving state exploration, and we did. And many papers were written doing this. And so this was a demonstration. You know, it used to be that a lot of the papers in CAV were kind of theoretical, or were for very small, almost toy-like systems. And this was the thing that showed we could actually do larger systems. Although the problem with BDDs is that they blow up. And so it often required some substantial cleverness to figure out how to represent your problem in a way that could be effectively solved by S&V. Nevertheless, that could be done frequently enough to make a big difference and to establish the credibility of the technique.
Can I quote to you a famous computer scientist?
Sure.
BDDs are temperamental. Say David Dill some years ago.
I didn't know that I said that, but
Yes, you
that's a
did.
great quote. That guy is smart, I'll tell you. Okay. It sounds like maybe Amir said it, but anyway, he was really smart. So, and then one of the demonstrations was the Gigamax cache coherence protocol. So at the time, shared memory multiprocessors were new. Now, I think every cell phone is one. Okay, but they were research projects funded by DARPA. In fact, that's how I got my first funding at Stanford. I got some from NSF and some from DARPA, working on the Flash project, which was mentioned earlier. And I went around the building and said, what's the biggest problem? And they said, the correctness of these cache coherence protocols. So I wasn't surprised to see Ken working on them, given that he knew what was up and knew hardware. These things were notoriously buggy. You know, if you ask somebody what kept them up at night, cache coherence protocols were likely, and they're a hardware designer, cache coherence protocols were likely there. So Ken and Jay Schwab of Encore Computer Corporation verified this Gigamax protocol using symbolic model checking. And as I recall, I'm not sure this is 100% accurate, but I think that was like one of the first successes of actually proving the correctness of reduced model for cache coherence. They found several subtle bugs. I went through the paper again in preparation for this. And the paper, interestingly, was not published in a verification conference. It was published in a computer architecture conference. And I learned something from this, right? That it was interesting when you're doing research in a practical area to find people who have the problem and may not care about the kind of solution you're working on, and try to demonstrate that you're actually really able to solve the problem that they care about. And so then you have the audience of your peers and competitors like CAV, but then if you're doing something like networking protocols or something like that, there are people in networking conferences who will want to hear that you could solve the problem they care about. And you hope that they actually do care about your paper to solve their problem, because you're trying to solve their problem. Okay, I've only got a few lessons. I got a very short amount of time. So I mentioned that Ken had some other significant research accomplishments, and I can't even talk about them all in the time I have. I can barely talk about this one, but this is a totally different one. So at the time, in around 1989 and 1990, people were getting interested in formal verification of finite state systems where there was lots of concurrency, and they noticed that it seemed like the current methods were inefficient because there was redundancy in the states being analyzed, because you have actions that commute pretty much independent in a concurrent system. And there's no reason to look at every possible interleaving of these actions. If you're smart, you can look at maybe one interleaving and see whether your property is satisfied or not. And so there are a lot of cunning and subtle algorithms proposed for doing partial order reduction. But Ken had a unique approach to this, and he applied it to Petri nets, which are generalized finite automaton, which capture concurrency explicitly in the structure, in case you haven't seen one. I was going to animate one, but I obviously didn't have time to do that. So Ken published this startlingly original approach to partial order reduction, which is called Petri net unfoldings, where you just stop. Where you unroll a Petri net in a certain way until it's unrolled enough, a finite amount. And there's this paper that I re-examined. I read it when it came out and re-examined it as I was preparing this talk. This paper is beautiful. I mean, the clarity of the exposition and the depth of thought that went into it, not to mention the originality in solving the problem this way, it's just really, really impressive. And I'd recommend anyone read it. This basically started a whole new branch of research. You know, I looked at some of the references to this. There's a book written on unfoldings for distributed systems of timed automata. I don't know what. So it started a whole subfield. And so I am running out of time, and in respect to our need to finish, I'll just mention that at the end of the PhD program, Ken, I hope this is, I don't, threw all these results into a bucket which he called his PhD thesis. It was a very, very well-written bucket. I don't know how much rewriting he had to do. That wasn't exactly stapling the things together. And nailed the ACM Doctoral Dissertation Award quite deservedly, because during this time, he had basically revolutionized automated formal verification while in grad school. And so he emerged as one of the leading researchers in formal verification, like 2 years into the graduate program. He basically created the field of symbolic model checking, which now has gone well beyond BDDs to other types of representation, symbolic representations of state spaces. His approach of using the theory and combining with practice and doing real examples gave the field credibility. And there were other major contributions during the same time. I mean, it would have been enough to do symbolic model checking. That probably would have won an ACM dissertation award, but that wasn't enough for Ken. And his career since has been a continuation of the same kind of amazing productivity and deep insight. So I'll just stop there. Thank you all.